Hi, in this video we are going to determine the electrical field intensity at this infinitely long straight line of charge. The charges are distributed uniformly upon this line charge, and the charge density of this line is represented by rho saba. Okay, we are going to solve this problem by taking the advantage of Gauss's law. Gauss's law basically is determined like this. Gauss's law states that the net outward flux of the electrical field or the net flow of the electrical field through a closed surface equals the charge enclosed over the permittivity of the free space. Now, since this line is infinitely long, the electrical field due to this line is going to constitute some shape like this, or the Gaussian surface due to this line charge is going to be like this cylinder, okay? And the electrical field is going to be radial. Just assume that this is the radius of this cylinder. This blue line is the radius of this cylinder, okay? And the electrical field is going to be along this line, radial, okay? Now, according to this, we know that the electrical field is radial. Okay? Now, and this surface is the surface which the electrical field flow through. Okay? We want to find the equation of this surface, then plug the surface and the electrical field both in Gauss's law. This surface ds is the surface of this cylinder, okay? Now ds, which is vector also. Now the unit vector of this surface is perpendicular to this surface, which is intuitively also radial, okay? Now as this surface is cylinder, and now this surface cylinder, we are going to use the cylindrical coordinate system to determine the equation of this surface. We will represent this differential surface, we'll represent the length of this differential surface by this small differential length, dz, okay? And the radius is constant in cylindrical coordinate system. We have three components, which are r, phi, or the azimuthal angle, and z. Okay? R is constant, as we said. Z is also determined. The azimuthal angle is this angle. Okay? And to represent this azimuthal angle more, I am going to take a cross section from this cylinder down there. You see, this is the base of this cylinder. It's going to have this differential azimuthal angle, which is d phi. Okay. Now, the area of the surface of this cylinder is equal to the length of this hypothetical cylinder, which is dz in this case. Okay, I'm going to use the green color, dz, times the area of the base, which is a circle, and the area of the circle is equal to the radius r times the azimuthal angle, this angle, d theta. Okay, and now r is constant. Okay. And because r is constant, I did not determine differential r. I did not say that I did not represent r with the prefix d. Okay, and dz. Let's say that this hypothetical cylinder has length of L. Okay. Okay. Now dz. Let's say let's say that this cylinder has the length of L, Okay, now this dz, the differential height, is ranging between 0 and L. Okay, good. And the azimuthal angle, which is this, is ranging between 0 and 2 pi. Okay, now we are going to plug these two parameters into this equation and apply Gauss's law. And now this integration is with respect to the surface. Okay, so it's integration with respect to two dimensions. The dimensions that we have down there is z and phi, which are ranging between 0 to L and 0 to 2 pi respectively. Now add these double integration. Okay, and to the right hand side, Q is the charge enclosed in this line. In this case, we are considering only this area bounded by this hypothetical cylinder. The charge in this part of the line of this infinite charge line is equal to length of this charge, which is L, times the charge per unit meter, or the charge density of this line in this area, which is rho sub. Okay, now Q is rho sub, which is coulomb per meter, times L, which is meter. The answer is going to be, the multiplication is going to be meter at the end. Okay, divided by epsilon. Okay, that's good. Now we are going to solve this integration. We are going firstly to integrate with respect to z, then integrate with respect to 2 pi. Okay, and when we take the integration with respect to z, firstly, these vectors, unit vectors, are going to be eliminated. Okay, now E sub r and r are constants. The integration of dz is going to be z, ranging between L and 0, and the integration of phi, if d phi, is going to be phi, ranging between 2 pi and 0. Okay, now this is going to be L and this is going to be 2 pi. I'm going to rewrite them. Okay, now substitute. Now divide both sides by RL by 2 pi RL, and ER is going to be equal to. Okay, that's good. And now this is the electrical field with respect to this infinite, with respect to this infinite line charge. Now I am going to, in order to write this electrical field with vector notation, we are going only to substitute this for this equation. And the answer is going to be. Okay, and that's the end. See you in another video.